finding zeros of polynomial functions. Now, zeros, all that means is roots, they're called. It's solutions to this right here, this f of x equals 0. Now, if you remember, f of x and y are the same thing. So that's when y equals 0. Now, on a graph, those points where y equals 0 are stuff like this and that. Those are called x-intercepts. So when I say zeros of a function, that's what I'm talking about. I'm talking about what x's give me y equals 0, or what x's are intercepts on the graph. Okay, that's what we'll be talking about this next whole section, is those zeros. Okay, one of these theorems, this theorem right here, helps us figure out what those functions are. It says that every rational is whole numbers and any number that can be written as a fraction of integers. Stuff that's irrational is square root of 7 or pi. Those kind of things are irrational. If it is a rational zero, then it can be found by computing this right here, listing all the values to where it's the factors of the constant divided by the factors of the leading coefficient. Now, the constant is the number without a variable. W/O means without. And then the leading coefficient, which I usually just write LC, is the number in front of the variable with the highest power, with a degree. Now, when it comes to calculating or listing them, sorry, we're going to make a list of everything. Comes to listing these, I would start with identifying your constant. So our constant's 20. And I'm going to list the factors of 20. Now, I'm not talking just prime factors. I'm talking about numbers that when you divide it into 20, you get a whole number back out. So does 1 divide into 20? Yeah, 1 times 20. Does 2 divide into 20? Yep. Does 3? Nope, going to skip 3. Does 4? Yes. Does 5? Yes. 6? No. 7, 8, 9, 10? Yes. 11, 12, 13, 14, 15, nope, I think that's it. And then 20, of course, divides into itself. So these are all the numbers that if I were to divide it into 20, it would come out to be a nice round number. Okay, now the leading coefficient is this guy out front, which is 1. That's always the best when the leading coefficient is 1. 1 only has one factor, it's a 1. So to compute, we call them the P's and Q's, right? P over Q. You're just going to combine all possibilities of these red factors over that orange factor. And there's only one orange factor. You always just start with taking all of your factors, all your P's, and writing them out and dividing them by that first one. So we'd have 1, 2, 4, 5, 10, 20. And then in the denominator for each of those is that 1 from Q. Now that won't always be that simple where it's a 1, like maybe if it was a 2 out in front here of the x cubed, then it would be a little bit different. We would have more factors to share. But in this case, we don't. So right now our P's and Q's can be listed as 1, 2, 4, 5, 10, and 20. Now before we move on, think about this for a second. If 1 divides into 20, does that mean negative 1 divides into 20? Sure, negative 1 times negative 20 also multiply into it. What about 2? Yeah, negative 2 divides in, it would give you negative 10. So anytime you have a factor, a positive factor, the negative one is also going to be part of it. Now, I don't expect you to list them all out. All you're going to do is throw a plus or minus in front of every factor. Every P and Q, there's always a positive or a negative possibility. Okay, that right there is a list of possible, now hear me say that word, possible. This isn't a list of solutions. This is a list of possible rational solutions. And it's going to come in handy when we start finding these zeros because you kind of have a starting point. It says here, try these values first. Okay, here is a graph of that function we just did all the P's and Q's for. And then remember I said that x-intercepts are zeros. Zeros are the same thing as x-intercepts. And it looks like we have one right here at -1, one right here at 4, and one right here at 5. So on the previous page, we listed our P's and Q's, plus or minus 1, 2, 4, 5, 10, and 20. Is -1 in that set? Yes, it is. Oops. Is 4 in that set? Yep. Oh, dang it, I touched the graph and moved. Right there. We're good. All right, and then 4 is in there. Absolutely, and so is +5. So I guess it's another way to verify also. You can say, okay, did I find the right ones? Did I graph it correctly? That's just a rational roots theorem. That's what that one's called. Okay, the next theorem that's going to help us find these things is called the fundamental theorem of algebra. Big words. It says every complex polynomial, oopsie, sorry, trying to fix this so it doesn't move again because that's annoying. Like, totally annoying. Okay, fundamental theorem of algebra. It says for every complex, okay, every complex polynomial function with a degree n, which is positive, it's not a polynomial if the degree is negative, has exactly n. Now here's the key part. Has exactly n complex zeros, some of which may repeat. So what this says is if you can find the degree, that is the number of zeros you need to find. That's what the fundamental theorem, and I'm kind of, there's more to it, to the actual theorem. This is kind of me writing it in a way that you would understand a little bit better. Notice this word complex in here. Complex numbers are the ones with I, and I don't know if you remember, but technically every number is a complex number because it can be written as plus 0i. So keep that in mind as we start solving these, is that it can be a complex number as well. Okay, so what you're going to be doing is on some of these, you're going to be looking at the graphs to find some of the zeros. But first, we want to identify how many zeros we're supposed to find. Well, the degree is 3. So how many zeros, or x-intercepts, or solutions, are we going to find? 3. Okay, looking at our graph, I have an x-intercept there, one there, and one there. So my zeros are -2, -1, and 2. So from a graph and the function, you can tell how many zeros you need to find, and then look for x-intercepts, and those are going to be your zeros. Make sure the function is set equal to 0, the equation. If I give you an equation and it was like x to the fourth plus 2x equals 2 or something, you would need to move that over before you could solve it. You're usually going to be given to them in fx form, and then we would be adding the equal 0. But just in case, make sure everything is equal to 0 before you graph it. And then you're looking for x-intercepts. Okay. Find all zeros of the polynomial function. Okay, let's identify some pieces of it. 3 is the degree. Leading coefficient is also 3. Constant is -1. And then the question is, how many zeros? Well, if the degree is 3, that means there should be 3 zeros. Now, I can look on the graph and I can tell you right away that -1 and 1 are zeros, right? So identify the graphs using the zeros. I can tell you 2 of them right now. But that third one right here, I'm not sure. Like, is that a half? Is that, is that -1/3, -1/2? Maybe it's -1/4. I'm not really sure. That's where that rational roots theorem comes into play. If you go through and find all your P's and Q's, so P are the factors of the constant, so factors of -1. Well, there's not too many of that, right? Plus or minus 1. Okay, and then we're going to go in and say, okay, our Q values are going to be factors of 3. Not very many of those, right? Plus or minus 1. 1 is always one of the factors. And then the number itself is also one of its factors. So our possibilities here are P over Q, our possible rational zeros are all combinations with +1, so 1 over 1 and 1 over 3, or maybe it was -1 over 3, +1 over -3. Whoops. And you can go through all these lists, right? Then maybe there was -1 over -3. You can go through all the whole list, but it's simpler just to find the basic 1 over 1 and put a plus or minus in front of it. Basic plus or minus 1 over 3. So you don't even need to list all of these. You just need to take the P with that Q and the P with that Q and put plus or minus in front of it. So we've got plus or minus 1 and plus or minus 1/3. We'll look right there. Plus or minus 1, we got those already. Now our third choice, for our third one, our choice is either +1/3 or -1/3. Looks to me like that's probably -1/3. It's not +1/3, it would be on the right side. So in this case, we could get all the zeros, not just from the graph. We had to list out the possibilities to find that third one that we weren't quite sure about where it was at. Okay, let's look at these ones. These two graphs right here. They have a little bit, something a little bit different between them. Now the graphs look weird because they're cut off, but imagine down here somewhere in Never Never Land, the graph keeps going, right? Up here somewhere, the graph comes and connects with each other, whatever. So what we're looking at, though, is the zeros, the x-intercept. These guys, this guy has zeros at -2, -1, and 2. This one has zeros at -2 and 2. Those are considered x-intercepts, right? And then, of course, all those are x-intercepts. Well, according to our fundamental theorem, our degree is 3, so we should have 3 zeros. Is that how many we have?